Our last chapter together. Oh, sad, sad, right? We should all sit together and perhaps sing Kumbaya. Hold hands. Chapter 10. I love teaching chapter 10. First of all, I got some cool demos to show you, which are always interesting. Unfortunately, we don't have as much time as the Tuesday, Thursday people. If we had a little more time, I could show you some more demos. But everybody has some common experience in gases. And so that's why I like to teach chapter 10, because everybody has a basis for comparison and some ideas as to what is involved in gaseous behavior. All right, so let's compare gases to liquids and solids, because you have to change your paradigm of perception when you're talking about gases. Up to now, we've talked mostly about solids and liquids. Now, gases have a different paradigm, and even though we have some common experience, let's review in the context of our common experience what that means. Gases are different than liquids and solids because they will expand to fill their containers, right? If I take some volume of liquid and I pour it from one container into another, it will take the shape of the other container, but the volume does not change, right? The volume, if it's 1 liter from one, it'll be 1 liter in the other. It's simply the shape that's changed. A gas is completely different. I've got a butane lighter here. If I take the butane lighter and I simply open it up and allow the gas to start escaping without flicking it and making the gas burn, I can allow the gas to escape by simply opening up the butane lighter. The gas escapes this tiny little container, and it will expand to fill the entire volume of this room, right? There will be gas particles that mix homogeneously, as soon as they get between the other gas particles, right? In the room, and at some point I could test the concentration of the gas in the room, and I would find a few atoms of butane floating around in the room. So that's one thing that's a big difference between liquids and gases, is gases will expand to fill whatever container that they're in. They're also highly compressible, which means that you can smoosh them. In lab this week, we talk about the smoosh factor as one of your points of error, and that's one kind of invention of the idea. But thinking about a container that you can smash that has a gas in it, you know that the gas will shrink. That is the basis of an industry that is known as hydraulics. You may have seen hydraulics before if you've ever seen. For example, I grew up on the west side. There was lowriders, and lowriders, I think a lot of times they have hydraulics that are under high pressure. They have shocks. And at lunchtime, I went to Trevor Brown High School back in the mid-70s. And so at lunchtime, the lowriders would go cruise around the parking lot to show off their cars, and we'd all come out there and watch after lunches. Everybody would drive their cars around, and one side would go up and they bounce in, and the other side would go up and front and back, and it was so much fun. They go by and people would clap and stuff. It was the funnest thing. Lunch was a blast at Trevor Brown High School. There's also hydraulics in the doors of this classroom. If you look at the top of the door, there's a hinge at the top of the door, and the hinge is connected to a box. Now, every one of the doors in this classroom has to be a fire door. In fact, all the doors in this building have to be a fire door, because this is the chemistry building, right? And we have lots of potential for fires and explosion in here. So all the doors have to be these really heavy fire doors. And so they put them on this hinge. So when you push them open, you can feel that they're quite heavy. But as they close really slowly. And if you listen real carefully, you can hear, as it starts to close, it'll go, shh. So what is happening inside that box? All right, so here's the door. Looks something like this. And the box is at the top of the door. And the box has a hinge that is connected to the hinge of the door. Inside this box, if we could expand the box and look at the inside of the box, inside the box is a long tubular thing, and one end of the tube has a hole, and one end of the tube has a piston that goes in and out of this enclosed tube full of air. So there's gas particles, right, inside the tube that looks like it's empty, but there's actually gas particles in it. So when you pull the door open, the piston moves back, and the air will go in through this little hole, and it will pull in a bunch of air till the piston goes back. And then you go through the door and you let go of the door, and when you start hear it go shh, is when that compression will happen, and so the air molecules get closer together and it provides a little cushion, and as that piston then moves in this direction, the air molecules, of course, get closer together. It moves a little bit more, they get even closer together, the air molecules are real dense. A few of them will be allowed to escape, and this process we call effusion versus diffusion. And gases do both of these things. They effuse and they diffuse. Diffusion is more like perfume. If I took a perfume bottle at the front of the room and I uncorked it, the perfume molecules would start to expand in all directions. And the people in the front row would smell the perfume first, and then the second row would smell it, and the third row, and so on and so on. That's called diffusion, which is gas particles expanding to fill their container from the source of origin. Effusion is the gas particles going through a small hole, and so they all have to travel through it, and this is the basis for the hydraulics industry, is gases are compressible, right? And this is also why they tell you to buy nitrogen for your tires, but we've already talked about that, right? You don't want to buy nitrogen for your tires, you're not going to pay an extra. Doesn't do any good. It's certainly not worth it unless you fly in a plane. Okay. All right, so if we look back at our PowerPoint, gases also have extremely low densities. What are the units that we use for density of a solid or a liquid? What's the units?
Actually, two things. I'll answer the question first.
Okay.
Usually we use, liters or milliliters for the volume?
When we're talking about density, what are the units of density for solids or liquids? Grams per milliliter, right? Grams per milliliter. So how much a milliliter, which is a very small volume, right? A milliliter is a really small volume because we can measure the mass of a milliliter of a liquid or a solid. Now, a gas, if you only had a milliliter of a gas, there's not going to be enough gas particles in a milliliter to weigh anything really that you can measure. So you have to expand the volume to 1 liter, which is 1,000 milliliters, because the gas particles are sprinkled in there. And then if you have a whole liter, you might be able to you might be able to weigh the mass of a liter. You had another question?
Yeah. It's more about it's about some of the gases. What would things like fire be involved in? Would that be considered a gas or just more of a reaction?
Fire, I would call more of energy and exothermic reaction. It depends on what you're talking about. You do talk a lot about that in 152 when you get to thermodynamics. All right, I'm going to come back to this link in just a minute. Before we talk about that link, I want to talk about this idea of pressure. Okay? Pressure has to do, and the physicists give us this definition, pressure has to do with some force per unit of area, right? Some force per unit of area, and here they're talking about force of a column of air on some unit of area below. Well, that's sort of a nebulous kind of description, and that's hard to think about. What is the type of, you guys travel to school every day on a little cushion of air that you have to measure the air pressure of. What generally are the units that you measure the air pressure in the tires of your vehicle? PSI, which stands for pounds, right, per square inch. So pounds per square inch. So there's the force per unit of area. And there's lots and lots of different units to compare pressure in. There's PSI. There is also ATMs. There is millimeters of mercury. There's torr, which was named in honor of, I think his first name was Vermicelli. He was an Italian fellow that did a lot of experiments in gas pressure, so they decided to name a unit after him. There's pascals, there's kilopascals. The physicists usually like these because it takes into account more of this pure idea of force per unit of area. So there's lots and lots and lots of different units that measure air pressure, but it's always this idea of some force divided by the area. You will have to make conversions between the different units. So let's talk about what the numbers mean. If you got one ATM, this is going to be the most popular unit for your gas law calculations. You're going to want to change the majority of stuff into ATM. So 1 ATM is the same as 760 millimeters of mercury. Okay, that's another equal conversion factor. So that's one you can use as a conversion factor. There's another one that is kilopascals, I think is 101.2, I think, kilo, 101.7, I'm not sure.
What's the living
Kilopascals, I'm not sure of the exact number. You might be right, it's 0.325, maybe that's where I rounded it up to the 2. And what else? I think that's most of them. Oh, a 1 ATM is also equal to 760 torr. So 760 torr is the same as 760 millimeters of mercury. Right. So it's the same thing. And I think physicists, once again, also like torrs better.
What would PSI be?
PSI is pounds per square inch.
Do you ever use barometers?
The barometers generally measure things in millimeters of mercury because, and we'll talk about how a barometer works in just a
Watch and say millimeters or atmospheres.
Right, and today in your lab, you're going to be measuring pressure in atmospheres. We're going to have to change because the calculations work a lot better in atmospheres. All right, so this idea of pressure, you have to be able to make conversions between units, so you're going to have to practice that. And here's where this thing that we call a barometer comes into play. We talk about a barometer and the barometric pressure. That has to do with the air pressure around us. The air pressure around us, 1 atmosphere is 14.7 PSI. That means every bit of surface area in this room is being pushed on by 14.7 pounds of air. If you could take a column and you weigh that column of air that is all through our entire atmosphere, every square inch of surface on the planet is being pushed on by 14.7 psi. And when you go up higher in elevation, they say the air becomes thinner. Does that mean that the air molecules actually lose weight? They get really skinny? What do they mean when they say the air becomes thinner?
There's less pressure.
There's less pressure. Why is there less pressure?
Because you keep on more.
They're further apart from each other, so they don't hit each other as often, right? And so if there's less pressure, you actually expand a little bit. So if you want to try on a bathing suit and look your best in the dressing room, do it at sea level. Go up to Flagstaff, where it's about 7,000 feet, you're going to feel a little bit puffy because there's not as much air pressure smooshing in on you.
Like astronauts get taller.
Astronauts get taller. That's gravity. That's a lot of gravity. But if you watch, I love sci-fi movies. And one of the sci-fi things that they always do is they have astronauts out in space, in their space suits. And I remember I've seen a couple different depictions of what happens to an astronaut if they're out in space and something happens to their space suits. Like I saw one where the mask, the glass part cracked a little bit, and so there was air exchange, and it showed that they just kind of freeze dry, right? Okay, that might happen, but I think there would be stuff coming out of the suit, right? Because there would be almost zero air pressure outside the suit, and if there was a crack, sure, the air would come out, but some of the stuff from the person would probably come out very crack too, because it would be such a low air pressure. So it depends, and one of the really good movies that I saw was the one with Sandra Bullock where she was the astronaut. That was so good. Did you guys see that?
Okay.
What was that called? Gravity, thank you. That was such a good movie. And my son, the astrophysics, went to see it, and he said that his favorite part was when she was outside the ship and spinning around trying to get in, that's really what it looked like, that they had a good simulation model for what would happen in a situation like that in space and how things would be zipping around. So that was interesting. Or what was the one with, what's the cute actor that was always in The Bourne Identity?
The Martian.
The Martian. Oh, that was, all the science in that movie? Dang, that was good. Dang, that was good science in that movie. Remember when he exploded himself? When he exploded, he was trying to make water vapor, right? He was trying to make water vapor into hydrogen and oxygen gas, and then, exploded them to make the water vapor. And then the funniest part was when he came back to the screen, he was kind of smoking. He goes, wow, that was the only interesting experiment. He's like smoking after he got himself exploded. All right, I think we're done for today, pretty much for unit of pressure. And we'll continue on. Yeah.